I come from the surge arrestor industry. I have a background in electrical engineering, and about 2 years ago, I created my own business as a consultant, dealing with lighting performance and surge arresters. It's a piece of a large puzzle, right? So we can also say it's the tip of the iceberg. It's visible, but what is the iceberg? Iceberg is this framework, this large framework connecting all the physical variables. So the idea is to follow this red line for this webinar. If you're located in Indonesia, maybe this landscape is not so typical. This is important to make a clear distinction between the flash and the stroke. We refer to the return stroke as the visible flash propagating upwards. So we are interested in the downward negative. We call it downward because the step leader coming from the cloud is going downwards, but actually the visible flash is going upwards. And this return stroke peak current is actually the most influential parameter, which is responsible for lightning overvoltages on overhead line. The frequency of the lightning event, the frequency of occurrence, which is measured by the grand flash density. I think everybody here is familiar with the GFD, grand flash density, which is expressed in flashes per square kilometer per year. So here's an example of calculation, determination of the lighting parameters using our own software called I3CM LLS, where we have the possibility to connect different lighting APIs and determine the lighting parameters along specific assets. If you compare the results with the keraunic level, so you have 3.3 based on the keraunic level, and actually only 0.6 based on calculation determination. Of course, there we can discuss about accuracy and algorithms, how to apply this, but it's important to notice that there is a significant difference. However, in the event of a large lightning current and poor grounding conditions, this increased potential can exceed the insulator withstand levels. In general, for a shielded line, you have a higher probability to flash over the bottom because of the electromagnetic coupling factor, which is more stressful between the power conductor at the bottom compared to the shield wire. And this is important to make a distinction between the shielding failure and backflashover. You have the possibility to convert the top phase or the top phases into virtual shield wire by using line arresters. Once you understand the impacts of lighting on overhead lines, it's important to use dedicated tools. We are using Sigma SLP that we also distribute. It's based on the Monte Carlo statistical method. Lighting is a complex phenomenon which you cannot really predict. It's like playing a video games many times, thousands of times, to see the different possible outcomes. It's really a software which is dedicated for lighting performance improvements with a special feature for line surge arrestor implementation. The idea is very basic. You want to minimize the investment and you want to maximize the performance improvement. Whether we have gapped or non-gapped, this is the same technology. It's metal oxide varistors, which are used on overhead lines. The main difference is that they are used for a different reason, to prevent flash over, because we want to reduce the outages. This is quite important to understand. Once you understand how the residual voltage plays a role for lighting protection, you've understood 90% of the technology. If you have a look in the CIGRE technical brochure 855, there are 3 types of line arresters which are described. There are often questions about EGLA versus NGLA. There are strong strategic advantages of using EGLA. Some people might disagree with me, but to be honest, the market situation is a bit more complex because there are manufacturers who don't have this technology of externally gapped line arresters, so they are not going to promote something which they don't have, right? Being a consultant, I will of course recommend to engage with industry specialists. It's not always easy to have access to the latest information, to do the best practice. It's a bit messy at the moment regarding line surge arresters, and we are working on it. There is an important work going on for this new IEC IEEE standards that will combine EGLA and NGLA together. But there is often a confusion between the energy absorption capability on station class, which is mainly related to switching over voltages, and this repetitive charge transfer. That is a key rating for the reliability of line surge arresters. There is often, I think, this misconception that the line arresters will fail due to an excessive lightning discharge. Of course, it could happen. But if you want to prevent this to happen, this can be computed, this can be simulated. When it comes to line surge arresters, This is a little bit more tricky because the cost of the device could be higher than the surge arrestor itself. The data collection is not real time. Sometimes you need to go on site to collect it, and those lines are often in remote areas, hard to reach locations. Once you have this information, I mean, what do? I mean, you should rather pay attention to the manufacturing process and make sure that this does not happen on line surge arresters. You should not have moisture ingress after a few days of operation. But we have the possibility to detect failures. And this topic is actually addressed in this technical brochure 855. We also have developed a dedicated solution which can unlock possibilities by correlating the fault location system and the lighting location system. If the line arresters is properly designed, properly tested, properly dimensioned, properly installed, you should not expect failures, and you should look at effective methods to detect failures. You should dimension the surge arrestor in a different way. So with backflashover, you would expect much lower lighting discharge current through the surge arrestor. But for shielding failures, you might expect much higher values. My recommendation would be to specify a short circuit test, not only to cover bushfire risk, but also to cover the specific arrangement of line surge arresters when they are hanging from the conductor, or if they are integrated into the insulator string or hanging from the cross-arm. This is not a typical arrangement, and most of the short circuit tests are not performed following this arrangement.